Okay, in this video we are going to continue the Euler-Cauchy differential equations, starting with this example. What will happen is that we will have repeated roots. The problem is going to be what is the second solution, but let's solve it. And it is a Euler-Cauchy differential equation because the x squared, second derivative, x to the power of 1, first derivative, no x, no derivative. So that makes it an Euler-Cauchy differential equation. Okay, let's start with the characteristic equation. So 4m squared plus 8m plus 1 equal to 0. Now, this is wrong. This is not the characteristic equation. This was the rule when you have constant coefficient and the proposed solution was exponentials. In this case, it's x to the power of m, and the characteristic equation is different. According to the formula in the previous video, is this minus this. 8 minus 4m plus 1 equal to 0. So be careful, because I usually see this kind of error in the examination. Okay, so this is going to be 4m squared plus 4m plus 1 equal to 0. Okay, so let's do the factorization of that. I'm going to divide by 4, and then we will have m squared plus m plus 1 quarter equal to 0. Now, two numbers in which the addition is 1 and the multiplication is 1 quarter, well, that is very clear. M plus 1 half and m plus 1 half. Multiplication is 1 quarter and the addition is equal to 1. So we have repeated roots, because my first root is going to be minus 1 half, and that will be equal to my second root, which is the same as minus 1 half. Okay, so here the first solution then is going to be x to the power minus 1 half. And what about the second solution? What about the second solution? I cannot use the same number because that will make it linear dependent solution. So in the previous videos, when we have constant coefficients and my solution was the exponential of mx, the fix of this was only multiply. You take the same first solution times an x, and that makes it the second solution. However, that rule is not true here. So that was true when you have constant coefficients and the solution was exponential. So that is not the fix. So what we have to do is find the fix. So what is the methodology to get the second solution? Okay, to do so, then let's do the formula. Let's do the procedure to find the second solution. So I'm going to leave here, and I'm going to make the general case solution for the to find the second solution. So assume that you have this differential equation. You have ax squared second derivative plus bx first derivative plus cy equal to 0, and then your characteristic equation is going to be am squared plus b minus am plus c equal to 0. So the chicharronera is going to be minus b minus a plus minus the square root of b squared, b minus a squared minus 4ac, sorry for the space, divided by 2a, yes. Okay, now we will have repeated roots when this number is equal to 0, okay? And the m1 equal to m2 will be minus b minus a over 2a. So that means that my first solution, y1, is going to be x to the power of minus we can reduce this by a minus b over 2a. So that is my first solution, all right, in general case. Okay, now what we are going to do is to find the second solution using the order reduction formula. So the second solution using this formula. y2 is equal to w of x times my first solution where w of x, if you remember the formula, is going to be the integral of the exponential minus integral of p of x, differential of x, over y1 squared, differential of x. So we have to see what is p of x. Now, this formula was assumed with this kind of differential equation, but the first coefficient must be equal to 1. Okay, so don't forget this first solution. So let's write let's divide by 8x squared. So second derivative plus bx over 8x squared, first derivative plus c over 8x squared, y equal to 0. Now, when we develop this formula of order reduction, we assume that the differential equation, the first coefficient to be 1. So that is why I divide by 8x squared in the whole equation, and this number happens to be p of x for the formula. Okay, so having the correct p of x, actually one of the x cancels. Okay, so we can do that. Okay, now let's do the calculation of this w of x. So it's going to be the integral of, below is the first solution, and the first solution is this one. So it's going to be x to the power of a minus b over 2a squared, and in the numerator is going to be the exponential of the integral of minus b over a x differential of x, because one of the x cancels, alright? And then here, differential of x. Now, big integral here, the 2 and the 2 cancels because they multiply in the power. So it's going to be x to the power of a over a minus b over a. Alright, because it's the common denominator. Now, in the numerator is going to be the exponential of the minus integral. Now, the b over a, I can take it outside. B over a integral of 1 over x differential of x. So that integral is actually the natural logarithm of x differential of x. Okay, let's continue with the calculation of w of x. So w of x is equal to the big integral. Here is going to be x to the power of 1 times x to the power of minus b over a. So if we split here, this and this cancel, so that is 1, and then x to the power of b minus b over a in a multiplication. Now in the numerator, the exponential and the natural logarithm cancels as long as we pass this to the power. So this is going to be x to the power of minus b over a differential of x. Now check that this number and this number, they are actually the same, so they cancel. So the only thing that is left is the integral of 1 over x differential of x. So this is very simple as the natural logarithm of x. So what is that? That is actually my w of x. Okay, so my second solution is going to be w of x times my first solution. So it's going to be the natural logarithm of x times my first solution, x to the power of a minus b over 2a. So engineers, the fix is multiply a natural logarithm of x. So in the previous method, the fix was just to multiply an x. So now in this case, the second solution is the natural logarithm of x. So now that we have the fix, the solution, how to fix this, then I can write the second solution here. Okay, so my second solution is going to be the natural logarithm of x times x to the power minus 1/2. Okay, and that's it. Okay, I don't have a space, but I'm going to write it here. The homogeneous solution, I'm going to make an skip from here to here. The homogeneous solution then is equal to c1 x to the power minus 1/2 plus c2, the natural logarithm of x, times x to the power minus 1/2. We can factorize the x to the power minus 1/2, but it's still the same. So this is the solution. This is the solution of this kind of Euler-Cauchy differential equation when you have repeated roots. Again, the fix is just multiply the first solution times the natural log of x, and that's it. Okay? And here is the demonstration why it is going to be always the natural log of x as long as we have repeated roots. Okay, next video we are going to cover the what to do when we have imaginary roots. Alright? See you.